Hello and welcome to lecture 19. This is our third lecture in our unit on optics now that we're all done with electricity and magnetism. And we're going to continue talking about the wave nature of light, okay? And specifically how a single slit can create a diffraction pattern. Now this lecture is very much based on the ideas of double slit interference patterns. So if you haven't watched lecture 17 yet, I would highly recommend checking that out and making sure that you're familiar with that material because I'll refer to it occasionally throughout this lecture. So let's take a look at our objectives. We want to understand what happens when coherent light shines on an object with an edge or an aperture. Okay, and then that's the whole idea. The light's going to diffract. Okay, we want to learn how to understand the diffraction pattern. I'll obviously define what diffraction is and the diffraction pattern when coherent light passes through a narrow slit. That's the main focus, especially in the examples, the actual quantitative solving here. Finally, we want to refine our understanding of double slit interference, yet another reason to watch the video on double slit interference, to include the concept that each slit also has single slit diffraction that leads to an overlapping of two interference patterns. That's kind of the final idea in this lecture, is how do we take what we learn here about single slit interference and acknowledge that both of the slits in double slit are, after all, single slits, so they must also be undergoing single slit interference, which we ignored in lecture 17. Reasonably, we ignored it, but now we can't anymore. We need to acknowledge its effects. Okay, so let's take a look at the key terms. Diffraction is our first one. So what is diffraction? I'm zooming in a bit on this. It's a phenomenon, so it's something that occurs, of a wave. So all waves, whether they're sound waves, ocean waves, all undergo diffraction, okay? That states that after passing through an opening or around a corner, the wave will begin to spread out and fill in the empty space. So diffraction is really the way that every time you see a wave drawn, there's maybe some wave source, right? S for source. And we always show the wave kind of coming out like this. This is the typical symbol for like a speaker, for example. Well, what we're showing there is diffraction, right? We're showing the spreading out of the wave. Okay, that's exactly the idea of diffraction. So intuitively, we know that waves do that. They spread out. Okay, like imagine ocean waves passing through the opening to a bay. Once they go inside that bay, those ocean waves spread out to fill in the water. Okay. Now, why is that? How do waves do that? Well, it's all based on Huygens' principle. All right. Now, you may or may not remember Huygens' principle. It's kind of a technical idea from sound waves. It certainly is discussed whenever sound waves are presented in a physics class. But what it does is it's a simple statement with a rather complex series of consequences. But the statement itself, I think we can internalize. It says that a wave front is composed of an infinite number of wave sources. That's it. Okay? Well, what does that mean? Well, consider this wave front. Okay? Over here. We have a wave front passing through a slit. All right, this is our single slit, the focus of this lecture. And we can take that wave front and say that every little segment of that wave is in fact itself potentially a source of another wave. Oh, interesting, right? And here we're drawing, 1, 2, 3, 4, 5, 6 of them, but really there are an infinite number of them, just zoom in as much as you want, okay? And so since each of these is a source of a wave, it creates a spreading wave that comes out. And that explains the diffraction, right? Because look, we see that this spreading wave spreads out, creating this ability of the original wavefront to fill in the available space. Okay? So simply saying that any wavefront is composed of an infinite number of wave sources is all we need to explain the ability of waves to diffract. In other words, fill in the empty space after passing through an aperture, for example. Okay? Now, it turns out that Huygens' principle also explains the law of reflection, also explains the principle of refraction. So it's such a big series of consequences from just that one simple statement that every wavefront is composed of an infinite number of wave sources. Okay? Now, even here, there's interference because we think about each of these wave sources being an individual source, then there's going to be points of constructive interference, like this one I've just circled, right? Any place where these these red lines, which would represent a crest, okay? Whenever they overlap with another crest from another one of these wave sources, that would be constructive interference. There would be regions of destructive interference because halfway between any wave crest is a trough. So for example, right here, there's a crest on top of a trough, that would be destructive interference. So even just within this spreading out pattern, there'd be little individual locations of constructive and destructive interference between any two pairs of waves. Now that's the idea we're to come back to actually explain the pattern that would come from this phenomenon, say if there's a screen right here, okay? But we'll of course come back to that and define it more specifically in just a moment, okay? But anyway, here are the interfering wavefronts from those infinite number of wave sources. Okay, so that's the idea. And of course, that's an important idea because otherwise, how could a single opening create an interference pattern, right? Because now we see there's actually not a single thing. It's an infinite number of things, bunch of sources. Okay, so unlike kind of our real simplified idea of the double slit, strictly saying that it was just two sources, just two infinite sources, themselves, like, well, that's an idealization. You're never going to actually have a truly small enough source. Every source can be split into other tinier sources based on Huygens principle, okay? And of course, I mean a source of a wave. All right, so now let's get into really what we mean by single slit diffraction, okay? By the way, here's the pattern. Kind of good to just have that reality check. It looks like an interference pattern, right? Like that we saw for double slits. It's got a central maximum. It's got maximum off of that central maximum, your secondary and so on. It's got minimums between them, which are, locations of destructive interference. Some things do look different, okay? One thing is that the central maximum is a lot bigger comparatively to the subsequent maxima, and it's wider, okay? So there are some differences, but it still is an interference pattern, has a lot of similarities to double slit interference. All right, so that's a good thing to start on. But let's define it. Okay, so single slit diffraction comes from wave sources create pairs. Okay, we'll come back to the idea, between the top and lower half of any slit. And these pairs of sources all have the same path length difference, and thus they create an interference pattern on a screen, okay? So what we're doing is we're pairing up all those infinite number of wave sources based on Huygens principle. We're pairing them up between the upper half and lower half of any slit, okay? That's why we've drawn this midline along the slit, okay? There's the slit. The slit width is defined as A. You'll see that again in the key equations. And so if we considered, and each of these little diamond-shaped things is our idea of one of those infinite number of sources. So we would pair up, say, the one at the bottommost of the bottom half and the wave source at the bottommost of the top half. These two wave sources would pair up. And what I mean by pair up is that whatever interference those two sources are going to have with each other is going to be the exact same interference as the next pair. And then the pair above that will follow the same interference. And that means that all the behavior between the interference of the upper half and the lower half works together. That creates the pattern. That's why there's not just, say, random processes here, because that's not saying like, oh, well, yeah, sure, they interfere with each other, but they all interfere in a random way and it cancels out. That's not the case. No, it's a pattern, right? It's the bottom half working with the upper half of the slit, okay? Or working against it in the case of destructive interference. All right, so that's the underlying principle. That's why we have the equation that we have, which again, you'll see in just a moment in the key equations. So a couple of things of notice here that, again, are going to take us back to double slit interference is we have potentially the small angle approximation where we can, which is also shown up here, where we can say, okay, well, because the distance d is so much larger than the spacing between the maxima or the minima, that our triangle is almost like a straight line, so tangent theta approximately equals sine theta, which means then we can have a relationship where we don't use the sine functions at all in order to find the spacing between the extrema, in this case, the minima, actually. You can see conditions for minimum, okay? And the other approximation, the parallel ray approximation, is also here, okay? We're saying that this angle is equal to this angle because, again, we're assuming that the distance is so much greater than the actual slit width. Now, we're also always, just like we did in lecture 17, going to use the parallel ray approximation, but we're only sometimes going to use the small angle approximation, okay? So you can rest assured that these angles are always going to be the case, so our idea of path length difference is always going to hold, but sometimes we're actually going to use the sine function in order to solve for our angular displacements to minima. Other times we're just going to use this relationship here, okay? All right, so now again, it will become clear in the examples because I'll show cases of both. All right, so there is our single slit diffraction pattern. And let's just pause real fast and appreciate the name of it, because we call it the single slit diffraction. Whereas, if you remember, the key term back in lecture 17 for our very similar interference pattern was double slit interference, okay? Now, those names are subjectively chosen. We could call this single slit interference because after all, it is an interference pattern. The only reason it's called single slit diffraction is to call attention to the idea that it's all these little infant wave sources from Huygens' principle that actually lead to the interference pattern. So the name is just there, just kind of used by popular vote because of the way that it calls attention to the phenomenon of diffraction. To be fair, double slit interference also is based on diffraction. I suppose we could have called that double slit diffraction. No one does. They all call it double slit interference. So really, you could call that's diffraction and interference are involved in both processes. Okay? Hopefully that's clear. Now, our last key term here is single slit envelope. What the heck do I mean by that? What's a single slit envelope? Well, an envelope is one function on top of another. That term comes up sometimes when we talk about an exponential envelope. But here, basically, we're putting one curve, one sort of sine function on top of another. Okay? But why? Why would we do that? Well, let me explain. Okay? So here's the first term, our first sentence. The single slit envelope is just the result of considering the combined effects of double and single slit interference. Okay, so this refers to our third objective, if you remember from a minute ago. Okay, so that's all it is. It's just combining the effects of single slit and double slit. Okay, and what it means, or what it results in, is a more realistic, that's good, interference pattern for double slits. Okay, because again, before we idealized double slits in lecture 17 as pure single sources. Okay, but now we're not. Now we're going to actually treat them as actual slits. Okay, so let's consider real fast. There's a neat little diagram down here that I'll run through. So in part A of the diagram, this is a single slit diffraction pattern. Okay, yes, an interference pattern. Okay, it's got that big central maximum. On the vertical axis is intensity, just showing that this is a big bright central maximum. Here's our secondary maxima here. All right, we have our locations of minima. All right, so we have a minimum here, right? We got a minimum for a value of 1. See, that's an m of 1. All right, d here is just a subscript denoting minimum. Here is the second minimum. So this would be the primary minimum and the secondary minimum. All right, same thing over here on this side, primary minimum on the left and secondary minimum. Okay, so that's the pattern that comes from single slit. Now, if the single slit was one of two double slits, then there would also be the two slit interference pattern. Okay, the one separated by some separation distance d. Okay, and here we're saying that that separation distance is 4 times the width of the slit. Well, in that case, the diffraction pattern or interference pattern from the two slits would look like this. It would have that one central maximum, okay, and then it would have lots of subsequent maxima. All right. Now we're not showing them getting any dimmer. We know that before we showed the secondaries getting progressively less tall, right? Maybe something like this. Okay, but regardless, they would be spaced like this, and it is realistic that they'd be much tighter together, because almost counterintuitively, the pattern from a single slit is really spread out on a screen, whereas the pattern from double slits tend to be very closely packed together. And you might be like, but the spacing is bigger on double slits. Wouldn't that make a bigger pattern? Well, no, because in both cases, it's an inverse relationship. The spacing always ends up being in the denominator of the equations. So the smaller the spacing, the bigger the pattern. So that's why single slits, obviously single slits having always narrower widths than the spacing between slits, in this case 4 times more narrow, it means that their patterns are always more spread out. So the way that these patterns are comparatively tight and spread is almost always the case in a real experiment or a realistic situation. But now finally, the envelope, the combining them together. So the calculated intensity pattern, and we're not going to talk about the equation, how to calculate this intensity, so think of this as more qualitative. For the two slits of width A and separation distance equal to 4A, right, so 4 times wider than the individual slits, including both interference and diffraction effects, looks like this, all right? And there's the envelope of the intensity. So we see that there are maxima that fit within the single slit diffraction, all right? And there's a point where there would be another maximum right here, a maximum from the double slit interference pattern, but it happens to fall exactly where the minimum from the single slit diffraction pattern is, and that means that it's not there. we lose one of the maxima that would exist because the single slit effect cancels it out. The envelope means it can't be there. Because basically all the maxima from the double slit pattern, they will exist as long as they can fit inside the envelope, and they're restricted by the envelope, right? Their heights are restricted by the envelope. Okay? All right, so that's the idea of combining single slit diffraction and resulting interference with two source or double slit interference patterns. Okay? All right, and we'll actually do one of our examples on this very idea. Okay, so now let's finally look at our key equations. Okay, so our key formulas, there's just two of them, right? They look pretty basic, and indeed they are. Oh, actually, I'm jumping ahead. I wanted to show you one other figure over here. This idea again of combining single and double slits. So let me pop that in. There we go. Okay, so I just want to point this out because this could be a potential concern, right? And if you haven't thought about it, that's fine. But if we are combining the ideas of double slit and single slit, how does that work, right? Because I mean, which of the double slits is the single slit? Like how does that? Well, we're kind of assuming that both of the slits of the double slit is behaving like the single slit, okay? Because they're close enough together and they're both further enough away from the screen that we can absolutely do that. They all have the same angle, okay? So that's the idea, is that if we were to consider the single slit being the lower of our pair of double slits here, because they're separated by some distance d, right? And then each slit has a width a, all right? Just like we've been talking about, and you're going to see in the key equations, that if I was to make a triangle for the angle of the single slit to, say, this point, and then I also made a triangle from the angle of the middle of the double slit, as we do, to that same point, I'm going to assume that this angle, I'll zoom in so you can read them, this angle theta double and this angle theta single are the same, all right? And they're the same by that ubiquitous parallel ray approximation, all right? So that means that we really can combine the ideas without worrying about incredibly complicated geometry, all right? Are they exactly the same? No, but they're so close to each other that we can definitely make that reasonable approximation. Okay, all right, good. So now let's finally move on to the key formulas. So the first one here, this formula, this is the main formula of this lecture, is the condition for destructive interference for a single slit. And notice, unlike in lecture 17 on double slit interference, I don't have an accompanying equation for the condition for constructive interference. Because although we can reasonably say that the constructive points, the bright fringes, are halfway between any of these minima, we don't really calculate them. They tend to not actually show up. It becomes a little bit messier of a calculation, and it's just not the way it's done for the approximation reasons, but also for another reason, because of the way we count them. Because notice this formula has m in it, right? That idea of counting the order of the minimum. Well, here we count m a bit differently. M is going to start at 1 instead of 0. And so because the closest minimum are the ones on either side of the central maximum. And I guess the most important thing, the biggest reason we do this, is because the maxima have one oddball. Because before, all the maxima are the same. They all have the same width and they're all spaced equally from each other. And before, I mean for double slit interference. But here, the central maximum is twice as wide as any of the other maximums. It's effectively two maxima fused together as one. And because that central maximum is twice as wide, it doesn't really make sense then to find the locations of the other maxima, because they would be like 1.5 distances away. Okay? So instead, we start with the minima and we count from there. But there's no zero minima. Instead, there's just a first minima. Okay? All right. So that's the idea. And again, you'll see it in practice, and you just have to commit that to memory. Okay. So theta is the angle from the slit midline to the mth minimum. Okay. M is the order of the minimum. As I said, there's no 0th minimum, so it starts at 1. So that means if I plug in m equals 1, I'm finding the minimum that's right on the side of the central maximum, that big prominent central maximum. All right. So I'm finding the edge of the central maximum if I plug in an m of 1. Okay. Lambda, of course, is the wavelength of the light, and A is the slit width. Okay. A, it's measured in meters. That's actually the slit width. Okay, I know it's probably strange to use the letter A for a distance, but that's just a convention. Okay, all right, so there's really our main formula. Okay, there's no small angle approximation in this one. Okay, so this is the one that can be used all the time. Okay, but right below, I've got the small angle approximation, where we can say that sine of theta approximately equals tangent theta for angles that are less than or equal to 15 degrees. Now, tangent theta is exactly equal to y over d. Y is the distance along the screen to whatever minima you're interested in, all right, from the midline, and d is the distance from the slit to the screen. Okay, but I got a picture, all right, after I label those two variables. All right, and that picture is going to refer to the path length difference, because there's something really interesting going on with the path length difference. And you may have noticed it, because in addition to, as I mentioned, they only have this one formula for minima. You also may have thought, well, this looks more like a formula for maxima, because it's integer multiples of a wavelength. You might be thinking, well, last time I checked, if I have a phase length difference of 1 lambda, that's constructive interference, not destructive. Well, it's because the actual path length difference that is built into this formula is 1/2 of the path length difference is equal to m lambda. So in other words, m lambda here is not the path length difference. It's 1/2 the path length difference. Well, where'd the 1/2 go? It canceled with 1/2 a, because in the derivation of this, there was a 1/2 a. Why 1/2 the slit width? Well, you can guess from back in the key terms. It's because we're pairing up those infinite number of wave sources between the bottom half and the upper half. So the actual distance between any two of those wave sources is 1/2 a. So when we write this formula, there is already a cancellation of those two 1/2s. Okay, that's why it looks like a constructive interference formula. All right, and a picture. All right, here it is. Right, here's the two waves that we would be comparing. Right, for example, comparing a wave from the upper half of the, well, I should say the topmost wave from the upper half of the slit, and the topmost wave from the lower half of the slit. Okay, those are the two that I drew in purple here. I'll zoom in a bit more. Okay, so that, and the two path length differences would be R1 and R2. We're assuming they're parallel, right? Because that's always assumed. Okay, so then and we want that path length difference between R2 and R1 to be equal to 1/2 of lambda in order to get our first order minimum. Okay, yeah. So as long as they have that path length difference, when they arrive at that point on the screen, they're going to cancel out and create a minimum. Okay, and the distance from the midline of the slit is y. The distance from the slit to the screen is d. The angle is theta. Okay, the angle to the first order minimum. That'd be like theta 1. Okay, and then again, notice that then that means that that central maximum has a width of 2y. Okay. Okay. All right. Very good. I think we're ready to do our practice examples. All right. So let's take a look at let's first of all look at the two types, okay? Type 1 and type 2. So type 1 is most of them. Problems that involve the location or locations of interference minima, notice it's just minima, of the single slit diffraction pattern using the small angle and parallel ray approximation. Okay, good. All right. Now, actually, we're not always going to use the small angle. I meant to make that clear. This should not always say small angle. It should just say parallel ray approximation. I'm gonna update that in the version of the notes. It's just a copy and paste error there. If you'll bear with me. But because the point is that unlike in lecture 17, where I really called attention to, okay, here we're using the small angle approximation, making it clear. Here we're not using the small angle approximation. Let's clearly state that. Here instead, we're going to check for it. We're going to check and see if we should use the small angle approximation or not. Or to be safe, you could just never use it, because you can always use the angular case. Okay, just saves you a bit of calculation to use the small angle approximation. So I'm not splitting up the problems into those types, because we've done that before. And then here instead, we're just going to group all those problems together and figure them out case by case. Okay, so that's type 1. Type 2 are problems that involve locations of missing maxima of the two slit interference pattern due to the combined pattern of single slit diffraction, the combined pattern of the single slit diffraction pattern. All right, the single slit envelope. So this is where we're combining the two effects, the more realistic version of double slit. Okay, all right, let's take a look at our first example. You were asked to measure the width of a tiny rectangular opening in a circuit board, but realize that your calipers are not precise enough for the job. So how do you do it, right? Instead, you shine a green laser with a wavelength of 570 nanometers through the opening and carefully align with a whiteboard parallel to the opening at a distance of 3 meters. With the diffraction pattern on the board, you measure the distance between the two minima on either side of the central maxima as 10 centimeters. what is the width of the rectangular opening? So this is a really clever way to measure small things and quite accurate. All right, so let's see. So we're going to check for the small angle approximation here. All right, so we're going to look at our distance to our edges of the central maxima, which is our first order minima, right? Because either side of the central maxima is a first order minima, as I mentioned before. All right, and so let's see. So that's just going to be tangent inverse of y over d. We already know y and d, so we get 1.9 degrees. Well, that's definitely small enough to use the small angle approximation. All right, so then we're just going to go on to do that. Here is the formula for the small angle approximation. All right, and again, basically the same as the formula for the small angle approximation for double slit, just replace a or replace d with a. All right, and remember that this represents minima now. Okay, and then solve for the slit width. Solve for the opening of this rectangular hole in the circuit board. Right, by plugging our numbers, notice we are plugging an m of 1, right, because it's the first minima. All right, there's our wavelength, there's our distance to the screen, right? There's the actual spacing, and notice that it's half, right? Because I say that the distance between them on either side is 10. That means the distance from the midline to the first minima must be 5 centimeters. All right, or well, this should be meters too. That's a typo. Right, that should say meters. I'll definitely fix that on the upload of the notes. So if you look at the version of these notes, that will say meters. Right, I don't know why it says centimeters. Just dumb mistake. Right. Okay. All right, and there it is. 34 microns. Right, 34 millionths of a meter. Excellent. Right, and that's actually a realistic hole size. Right, just small enough you couldn't quite make it out with the naked eye. Okay. All right. So good. Hopefully that makes sense. Quick concept question. Question 1. The diagram shows a single slit with the direction to a point P on a distant screen shown. At P, the pattern has its maximum nearest the central minimum. Okay, just like the previous example. If X and Y are the edges of the slit, what is the path length difference? PX minus PY. So they're on the edges, the far edges. So look, that means I'm not comparing the ones that I've been trying to talk about. The ones I've been saying, okay, when we talk about the pairs of wave sources, if I wanted to compare a wave at the top of the upper half, I'd have to compare it with a wave at the top of the lower half. But instead, these two waves are the top of the upper and the bottom of the lower. So this is not the typical ways to compare. Interesting. All right, and this is giving us a minimum, right? So this is the pattern has a maximum nearest the central maximum. All right. So then what's the path length difference? Well, we know the first order maximum has a phase difference of 2 pi. Okay, that means that the path length difference between these two waves must be lambda. Okay, good. Okay, let's do another example. This one, well, is definitely not going to be the small angle approximation because check out these angles, right? So we have a second minimum. So this would be m of 2 over here. Okay, that's the second minimum. And that's at 45 degrees, so definitely not a small angle. And we want to find this angle for the m of 1, the first minimum, the minimum that's on either side of that big central maximum. Okay, so visible light of wavelength 550 nanometers falls on a single slit and produces its second diffraction minimum at an angle of 45 degrees relative to the incident direction of the light, which is also the midline of the slit. What is the width of the slit? Right. So, and then at what angle is the first minimum produced? Okay, very good. So first of all, we'll set this up, okay, and we'll acknowledge that it's an m of 2. Notice I'm not using the small angle approximation. All right, and then I'm going to go ahead and solve for the slit width, A. All right, and I already know theta, it's 45 degrees. I know the wavelength, so I can easily solve for this, okay? And what do I get? Once I plug in my numbers, I get that the slit itself is about 1.5 microns wide, so 1.5 millionths of a meter. Very good. Now, I'm going to use that value to find an angle for an m of 1, which is going to be the first minimum. All right, so now we solve for theta for m of 1. All right, so just set this up, and since I'm solving for theta, I need to do an inverse sine function. Here's that m of 1, replaced in the equation, and I get 20.7 degrees, okay? They're not evenly spaced. It's not half of 45. It's not 22.5, okay? They're never evenly spaced if you're not using the small angle approximation. The small angle approximation does give you evenly spaced minima, just like it gives you evenly spaced maxima for the double slit interference pattern. But the small angle approximation works only for small angles. Once you get big angles, the spacing is no longer evenly spaced, and you have to find it using inverse trig functions. Very good. All right, and then finally, what is the angular size of the central maximum? Well, all right, it would just be, oh, I didn't write it in there, whoops. it would just be twice of this, because if this is theta 1, all right, and I'll write it after the fact. But so if theta 1 represents this angular size of half the central maximum, then the angular size of the entire central maximum, so theta max, would just be 2 times 20.7 degrees, which is just going to be 41.4 degrees. And that would be that size, right, that angle right there, theta max. Okay, good. So that's part C. All right, finally on to example 3, our last example. Sorry, we don't have a lot of examples here, okay? It's because it's just a pretty standalone idea. Obviously, conceptually, it does take a bit to work with, but the examples are pretty straightforward. Okay, so example 3. This is our other type of example, combining double slit with single slit. So laser light of wavelength 500 nanometers. Here, I'll back up so it isn't distracting. So laser light of wavelength 500 nanometers illuminates 2 identical slits, all right, double slit interference, producing an interference pattern on a screen 90 centimeters from the slits. The bright bands are 1 centimeter apart, okay? And the third bright band on either side of the central maxima is missing, okay? Well, what does that mean? That means it's missing because of the single slit envelope, all right? So find the width of the separation of the 2 slits. It's find the width and the separation of the 2 slits. So we want to know what A is, and we don't want to know what D is. And we don't know either of those things. Wow, but we can find both. Pretty cool. All right, so here's the picture. All right, so here are our double slits, okay? This is our value of D, and then this would be A, okay? All right, and remember, they all share the same angle due to the parallel ray approximation. There's our distance to the screen, and there's our distance to our missing maxima, because we have our central maxima from the double slit interference pattern. We have our secondary maxima from the double slit interference pattern, but the third maxima, it's just gone, because it got canceled out from the first minimum, the m equals 1, of the single slit diffraction pattern. Aha, all right? So for double slits, maxima are located here, all right? And I'm not assuming small angle, okay? And for single slits, minima are located here, all right? Well, that's really interesting, right? See how the formulas are basically the same formula, but one means minima, one means maxima. We talked about why that is, right? Because of course, in the case of the single slit, it's because the 1/2's canceled, okay? But here are our 2 relevant formulas, all right? And we know that theta corresponds to an MD of 3 and an MS of 1. D here for double, S for single, okay? Doesn't it? You see, right? Because it's the third maxima that's missing, and it's the first minimum that makes it missing, okay? So that means that tangent theta is just 3/90, okay? All right, well, and, it actually doesn't mean it, but and tangent theta is just 3/90, because this angle, we know what it is. Now, I'm just saying we know the angle, all right? So let's go ahead and find it, okay? So it's 1.91 degrees, good, okay? So that means, I could use the small angle approximation, but I don't have to, because now that I know this angle, I can just go ahead and plug in and find A. Check it out, right? So then if I find A, then I find out that the width is 15 microns. That's the value of the slit width, okay? And then I know that because these two are equal to each other, I know then the D is just 3 times that. See? Because all I did is just plug in MS equals 1, and then if I just plug in MD equals 3, then that gives me this formula when I solve for D, just like I was able to solve for A, okay? And so we know it must be exactly 3 times as much, so it's just 45, right? So it's pretty neat. Just by finding out which of the double slit interference maxima has been canceled out from a single slit minima, you're able then to find the 2 widths, all right? Or the 2 distances, the slit width and the spacing between the 2 slits. Okay, all right, very good. Hopefully that makes sense. A neat little problem, light on the calculation, but heavy on the conceptual ideas. Okay, all right, well, I hope this lecture as a whole has been interesting and informative. Thank you so much for watching.